Hello, and welcome to Still Behind the Bench. My name is Adam, and on this channel I will attempt to describe the science behind distilling spirits in a more technical way. Hopefully it'll whet your appetite to learn more and teach you enough so that you're more self-sufficient. So for this video, I'm going to be talking about activated carbon. It might go a little bit long, but you should enjoy it. Let's get started. Most of you may have already seen activated carbon before or used it. Most water filtration systems have an activated carbon system in them. Aquariums do. Brita filters have activated carbon in them. But if you want to make legal vodka in Canada, you need to use activated carbon. If you want to make a flavorless vodka, technically you don't have to, but it's a lot easier if you do. So how does it work? Activated carbon is based on a principle called adsorption with a D. Adsorption is a surface phenomenon where a compound called the adsorbate sticks to the surface of the adsorbing material, the adsorbent. Adsorption happens because of two properties. One is the chemical polarity of the molecules in question, and then second is a specific type of intermolecular force called a van der Waals force, and specifically, since there are three of them, the London dispersion forces. So what is chemical polarity? In the simplest definition, it's whether or not a compound is polar or nonpolar. This is more of a gradient. It's not so binary. So depending on the conditions, something can be more polar or less polar. But polar molecules have what is called an electric dipole moment. You can think of it as like a magnet. So here we have a water molecule. Water is very polar. Thinking of it like a magnet, it has a north pole and a south pole. But in this case, one side of the molecule is more electrically positive and the other side is more electrically negative. In the case of water, it's a covalently bonded molecule, so the two hydrogens are sharing electrons with the oxygen, but there are two other electron pairs that are free. And so those two electron pairs will actually push these electrons down in one direction, which forces this side of the molecule to become more electronegative and this side to be more electropositive. And it's similar with other polar molecules. Now, London dispersion forces. They're a type of van der Waals force, as I said before, which are a set of weak intermolecular forces. The London dispersion forces are the weakest of them. It creates what is called an instantaneous dipole-induced dipole moment. What the hell does that mean? That's a complicated term. Essentially what it means is that when two nonpolar molecules, or a polar and a nonpolar molecule, get close, it can induce a polarity. One can induce a polarity in the other, and then the one that did the inducing forms a polarity itself. So let's just say we have a butanol, which is a 4-carbon alcohol, and we have the carbon wall here. Butanol starts to come up close. They're both nonpolar, so they're neutral. As the butanol gets closer, its electrons cause the carbon's electrons to move away. So now all of a sudden this carbon is polar. One side's more negative, the other side is more positive. At the same instant, the butanol also becomes polar as its electrons shift towards the now positive side of the carbon. So we have an instantaneous dipole-induced dipole moment. Probably makes a little more sense now. It's still complicated, but that's how London dispersion forces allow activated carbon to bond molecules. Now it's a very weak bond. A molecule can easily come in and hit it and separate them, and then they'll go back to being nonpolar again. One of the things about this is that larger, more nonpolar compounds have a greater affinity for the activated carbon than smaller, more polar compounds. So if we have our butanol here, if something like a decanol, which is a 10-carbon alcohol, if it came flying in, it would displace this butanol. It would get sent off wherever. It could be pushed further down the pore, or it could be knocked out of the pore, and the decanol would bond with the carbon instead. You may be surprised to learn that activated carbon is comprised almost entirely of carbon. 95 to 99% of it is carbon. The rest is called inorganic ash. So this ash are compounds that were originally in the source material. They pyrolyzed the source material. It's still full of inorganic material. That stuff doesn't combust, or doesn't pyrolyze, is what I should say. So what they'll do is called an acid wash, and it will dissolve a lot of the compound, but not all of them. Some of them are stuck deep down inside, and so typically between 5% and 1% will be ash. So all this carbon here is nonpolar. The intermolecular forces between that nonpolar carbon and the compound being absorbed will be higher, like I said, for larger nonpolar molecules. If you have, say, an acetone molecule, let's just say our acetone molecule is coming in, attaches to a wall inside one of the pores. Then an ethyl acetate comes in, That acetone will get pushed out of the way by the ethyl acetate because of the affinity for the larger and less polar molecule. I actually have a video of an acetone molecule going into the pore of an activated carbon granule and then it getting chased out by an ethyl acetate molecule. Let's watch. Just wow. The amount of money that scientists must have spent to capture that molecular chemistry on video in real time, that's astounding. So let's talk about the types of pores that are present. First off, you should know that pore size ranges are standards set by ASTM International, which was formerly the American Society for Testing and Materials. They changed their name, it's just ASTM International now. And then IUPAC, which is the International Union of Pure and Applied Chemistry. So pore sizes aren't just values that one country uses, they're international standards. So the first kinds of pores that we're going to talk about are transport pores. These are the larger pores. They facilitate the movement of molecules deeper into the activated carbon structure. Transport pores consist of two size ranges of pores. First we have the macropores, which are 50 nanometers and larger. And then we have the mesopores, which are between 2 nanometers and 50 nanometers. So nonpolar molecules sometimes will undergo London dispersion forces when they are within these pores, but the pores are generally so large, with the exception of when you get down to the smaller end of the mesopores, but they're so large that there's a lot of activity going on inside these pores. And so nothing really sticks around because you have so many colliding molecules. One other thing that can happen with these transport pores is that very large molecules, typically biomolecules, can literally get trapped in these pores for physical reasons. Just gets it lodged in there like Winnie the Pooh trying to get the honey. And it'll happen often if you have something like proteins in the liquid. So these transport pores lead to what are called adsorption pores, or you can just call them micropores because there's only the one. These pores are less than 2 nanometers in diameter, and because the diameter is so much smaller, a lot less activity is happening inside them, and so molecules adhering to the surface of these pores due to the London dispersion forces can be held in place with little issue. If another molecule does collide with it, it's just as likely it'll simply be stuffed further down the pore than it would be to be replaced by the incoming molecule or kicked out by the incoming molecule. You know, if we went down a list of simple alcohols, starting with something like water in the pore, methanol will kick the water out, ethanol will kick the methanol out, propanol will kick the ethanol out, and butanol will kick the propanol out, and so on and so forth, because as the carbon chain gets longer, these simple alcohols become less polar. That's just one way polarity manifests itself. So it starts off with a bunch of macropores on the surface. Sometimes the surface will have micropores as there as well, but they lead to the mesopores, and the mesopores shrink and shrink until they stop, and somewhere, usually littered all along, I wasn't going to draw them all, but all along it, there's micropores everywhere. There's millions and millions and millions of them. And just to give you an idea, these micropores are about 2 nanometers and less, but a water molecule is 0.27 nanometers, or I should say, the average diameter of a water molecule is 0.27 nanometers. So you could fit like 6 of them across just the mouth of one of the largest micropores, and then you could fill it all the way back. So you can fit not really a lot compared to how many molecules that the entire thing will hold, but a pretty significant amount can fall into a micropore. And water is one of the smaller molecules. But even larger molecules, they might only be, here, let me find an example here. Ethyl palmitate. It has 18 carbons in it, but it's a 16-chain carbon molecule. Its average diameter is only around 1 nanometer. You can fit a lot of these molecules into these micropores, and that's why they work. That's why it works so well as a filtration medium. So let's talk about the products that exist out there, why you would want to choose one over the other, and how the products are differentiated from each other. Okay, so let's talk about the products that exist out there. It comes in a lot of different forms, but I'm only going to focus on 3 types. Generally the ones hobbyists will come into contact with. The main type that people know about is granulated activated carbon. As the name describes, comes in granule form. Different mesh sizes, sieve sizes, which are the standard way that the sizes of the granules are measured. I'll get into that in a bit though. The second type is called powdered activated carbon. As you might surmise, it comes in a powdered form. If you're going to use this, wear a mask. And by that I mean something with an N95 rating, because when I say powdered. Sometimes it can be almost granulated, but sometimes it can be like dust. You don't want to breathe that stuff in. So powdered is more often used with gases, but it's sometimes used with liquids. You mix a bit in, stir it constantly, and then after a certain amount of time, it's left to settle and the liquid is decanted through a filter. The third type of activated carbon is extruded. What they do is they'll take a powder and they'll put it through something like a Play-Doh extruder, and it comes out in various shapes. The only shape I've actually seen though is just a little cylinder. Looks like little pieces of pencil lead that get chopped off. I don't really know a whole lot about extruded activated carbon or its abilities, but I know it's made of powdered, and it makes me wonder if it has the adsorbability of powdered, but the flowability of granulated. If that's true, it'd be a pretty awesome product, and I want to try it out to see if that's true. So now I'm going to talk about mesh sizes and sieve sizes. It's a pretty simple concept. Normally it only applies to granulated activated carbon, but technically it also applies to powdered activated carbon. So according to ASTM standards, powdered activated carbon is less than 80 US mesh or 0.177 millimeter. According to the industry though, it's smaller than 325 US mesh or 0.045 millimeters. And then the European Council has its own powdered value, 35 US mesh or 0.5 millimeters. I don't agree with this one because 0.5 millimeters is essentially the average size of white refined sugar, granulated white refined sugar, and it's granulated, it's not powdered. With granulated activated carbon, there are the same two ways it can be rated, either by sieve size or by US mesh size. Sieve size is the average width of a hole in the sieve or the mesh. US mesh size is how many holes there are per linear inch. So you take out a ruler, you measure it, you count 80 holes, it's 80 US mesh size. You measure the size of a whole bunch of the little holes, the width of them, take an average, you get the sieve size. Wikipedia has a chart for easy conversion between the two. The link's in the description. So if you're out on a website looking for them and you only have sieve size listed, you can find out the US mesh size if you're more comfortable with it. I'm going to focus on US mesh sizes as that's typically how I see it being sold here in Canada. But when you're looking at the activated carbon product itself, the product is usually based on using two different pieces of mesh or sieve to size it properly. So you may see a product labeled 8 by 30, 12 by 30, 12 by 40, 20 by 50, and any other numbers, because you can get them in custom sizes as well. So essentially what they've done is they'll have an upper mesh and a lower mesh. They'll pass the granules over. Whatever falls through the upper mesh but doesn't fall through the lower mesh, they will collect it all up, package it, and put 20 by 50 on the label. If it's a 20 mesh at the top and a 50 mesh at the bottom. If it's 8 at the top and 30 at the bottom, it's 8 by 30. 12 and 30, 12 by 30. 12 and 40, 12 by 40. So these three, 8 by 30, 12 by 30, 12 by 40, and 20 by 50 are the most common sizes you will find. But as I said, you can get custom sizes if you want to be able to have it in a different size, but I imagine it's expensive. So why would you choose one size over the other? Well, the larger the particle or granule is, the higher the ratio of transport pores to adsorption pores. So for a volume of activated carbon you're using, and say we were just packing this little piece of tri-clamp spool, the larger the granules you'll pack into here, the less absorption pores you're going to have versus a smaller granule that has less transport pores but more absorption pores, right? At the same time, you need to realize that smaller granules or particles pack together much tighter. So you may need more force to push the liquid through. So it comes down to what is an acceptable flow rate based on how you're using the product. If you're just using gravity, you might not want to go much finer than 12 by 40. You can try out 20 by 50, but it might just take too long. If you're able to pump it in or use a vacuum to suck it through, you might want to go with a finer material like 20 by 50. Okay, so the next thing I want to talk about is the source material used to make the activated carbon. Generally, it comes from a wide variety of sources, but I can really only recommend two of them. Coal here is a popular source, but I do not recommend coal as a source because, in my opinion, it's not food safe. A few decades back now, I think around 2002, 2003, there were some big issues with arsenic being found in coal-based activated carbon. And so its use fell out of favor with food-related purposes. And water. I know General Electric was one of the companies that had arsenic found in their coal-based activated carbon. So the coal-based will either be called bituminous or lignite, and sometimes it's called stone carbon, but it's all just coal. And so that previous issue that was discovered, and I think a lawsuit even happened, but came to a head around 2003. That's one of my problems with it. Another problem I have with it is that if you've ever looked into what's found in coal furnaces after they've burned it to, say, generate electricity, the ash that's left over is called fly ash, and it is just full of heavy metals and even radioactive materials. So I'm not so worried about the radioactive materials based on, how much we're actually using, but heavy metals being present in there kind of worries me. So that bridge is burnt for me. So the only two that I can actually recommend are coconut-based and wood-based. Coconut shell is, in my opinion, vastly superior to any other kind of activated carbon found on the market today. For some reason, it has the highest amount of micropores found in any of them upon activation of the coconut charcoal. I'm not sure why this happens, but it seems that something to do with the coconut shell allows it to have more micropores. Another thing about coconut is that it seems to be taking over the market because of all the other, coconut derived products, coconut milk, coconut oil. Then they use the coconut meat for things like Bounty chocolate bars and snowballs and all other kinds of coconut things. And then they're left over with all these coconut shells. So they turn them into coconut-based activated carbon. And it's a great product. So let's talk about how you'd actually use these great products. So with powdered activated carbon, the way I'd use it is you just pour it into a jar with the liquid, stir it around or shake it up every 10 to 15 minutes. Maybe do that for a few hours and then put it somewhere to settle. After it's settled, you just decant it through a couple coffee filters. You may need to do this more than once depending on how fine the powder is, but yeah, that's generally just how you use it. And you can do the same thing with granulated activated carbon. But for granulated activated carbon, the best solution I've found is just to make a housing out of tri-clamp spools and a pagoda, right? Hold on. So you have your tri-clamp spool, and what you'll want to get is what are called screened gaskets. So you can see there's a screen there. Don't remember what size it is. Think it might be 150. You don't need to get it that fine. You just stick it between what's called a pagoda. That's what this is. Stick it between the pagoda and the tri-clamp. Pour in your activated carbon and then get to work. That said, there's a guy on the internet. He runs a home brewing and home distilling store, and he's in Sweden. His name is Gert Strand, and he made I guess you'd call it a book, 25 pages I think, and it's about activated carbon, how to use it. It's pretty good. There's a bunch of things I disagree with, but one thing he mentioned was that a lot of distilleries pump the liquid in from the bottom. Just imagine this nozzle wasn't here. Pump the liquid in from the bottom and it comes out the top. Then you have, your other pagoda at the top here, and then it goes out to your collection vessel. So I asked a bunch of distilleries if they did that, and none of them said yes. But the more I thought about it, the more I figured that actually might be a better way to do it. Especially if you have a variable pump so you can control how quickly, or if you have a valve so you can control how quickly the fluid goes through the activated carbon, because you can better control, or I should say it's easier to control, the residence time that the liquid has in contact with the activated carbon. If you have the new make or whatever, your neutral, coming in from the bottom. And another way you could possibly do it, instead of pumping it in, so we have our thing, you might even be able to vacuum. So you pull vacuum on the top and the liquid will get sucked up and pulled through, and then run out this tube out to your collection vessel. Or you could have, this connected to some other vacuum vessel that acts as a liquid trap. Regardless, the idea is that pumping or having the fluid come in through the bottom would allow you to have the liquid in contact with the activated carbon longer, because the liquid is not being aided by gravity. You put it in through the top, it's going to flow through that as fast as it possibly can. You pump it in slowly through the bottom though, or you use suction to pull it in through the bottom, and you can have it sit there for a lot longer. The last main thing I wanted to talk to you about was pre-wetting. You'll see it mentioned on all kinds of forums. I imagine some distilleries also do it if they use a column-based filter like that. Pre-wetting is done in industrial chemical facilities. It's done in water treatment facilities. And they do it for a few reasons, all of which are related to pumping, process time, channeling, and safety. So not pre-wetting can significantly impact the efficiency of a pumped filter. If you're just using gravity and you don't wet, it's an easy fix. You just, after the liquid has gone through it and there's no more dripping out, just put your hand over the end if you have it open and just shake it up. That shaking will collapse any channels that have formed and it should move any air pockets to a different location, and then you can just do it again. But pumping and process time are linked, and the main issue is that air pockets forming can drop pump pressure and cause head loss, which is a significant issue. Pump pressure drops, head loss is formed. You may not be able to pump all the way through the filter, or it might just take a long time, especially if you can't force those air pockets out. But pumping in from the bottom, you might be able to force the air pockets out. And you may be able to prevent the wall effect, and you may be able to prevent channeling from happening. Okay, so last thing on pre-wetting is you do not have to use water to pre-wet the activated carbon. You can make a neutral, say 50% ABV, that's what I use. So I've done the activated carbon process, this kind, where it's in a jar. I used a gallon jar, and I did multiple fresh activated carbon filtrations on it. So I'm pretty happy that it's mostly just water and ethanol. But that's my pre-wetting liquid, right? I pour that through my filter when I use it. I haven't used it in a long time, but I pour this liquid through to pre-wet the activated carbon, or I dump the activated carbon into this jar and leave it there for a day or two. And then, if you're pouring it through, you just pour through and collect it and put the container away till you need it the next time. Then you just pour your new make through, whether it's a high proof neutral or you've diluted it down. And diluting it down can make it easier to filter stuff out because it can push out compounds that are normally dissolved in that high ethanol concentration. And when they've precipitated out, it's easier for the activated carbon to filter. The main point is that when you use this high proof pre-wetting liquid and you now pour your 95% neutral or whatever it is through, there will be less dilution than had you used water to pre-wet. Significantly less. I mean, it'll never go below 50% because that's what it is already. So that's the reason why I would suggest making what you call a pre-wetting compound instead of just using water. I guess that's it for all the main talking I wanted to do. There were two little tips, There are two tips I wanted to mention. Number one, when activated carbon gets used up, it is the micropores that get filled up mostly, and a little bit of the mesopores. And no, you cannot regenerate activated carbon at home with your kitchen oven or any other typical home appliance. Doesn't happen. Doesn't get hot enough, isn't oxygen free, and if you somehow did get activated carbon up to the temperature you need to regenerate it in an oxygen environment, probably going to start combusting it like coal in a furnace. All these activated carbon products aren't a one-time use thing. You can reuse them multiple times until you taste the result and see that it isn't working anymore. That's literally how I use it. And then, you just throw out that stuff and put in more. It's not super expensive. The only thing your kitchen oven is going to do is maybe cause water or some of the non-polar compounds found in the macropores and the upper part or the larger parts of the mesopores to evaporate out. And that could extend use a little bit, but it's not going to do a huge amount. So generally speaking, you can't easily regenerate activated carbon at home, regardless of who's telling you can. The second tip I wanted to give was that activated carbon can remove tannins from your spirit. So if you just happen to overage your spirit and it tastes tannic or astringent, you can put activated carbon in to remove some or all of those tannins. But you should know that flavor, color, and odor can also be stripped at the same time. So if you're sort of hitting the reset button, depending on how much you put in, you can try aging with wood again. You just have to be more diligent in taste testing it to know when you've hit the point where you have to remove the wood. As for how much activated carbon you should add when you're going to do this, I can't say. It's very dependent on how much liquid, how long you've aged, kind of wood you've aged. There's all kinds of things. But I would start with small amounts. So if you're using like a half-gallon mason jar, then just put in a teaspoon, shake it around for a few minutes, stir it for a few minutes, put it on a magnetic stirrer if you have one, and then taste it. And try again if it's not enough. It's going to take some experimenting to find out how much to add. The worst that'll happen is you'll just need to re-age it. And that's it for activated carbon. I'd like to thank our Patreon supporters for helping out, and please click like and subscribe if you want to see more content like this. And have a great week.